Here I will explain the topic related to second order low pass active filter using Sallen-Key filter. Second order low pass active filter using Sallen-Key filter. Diagram is two low pass filters are cascaded here. Consider admittance of the elements. This one is Y1, this one is Y2, and this one is Y3. Y4. Output of the filter is V0. Input to this filter circuit is Vi. A load resistance RL is connected here. For negative terminal of that op-amp is connected to two resistances R1 and RF. R1 here. This one is RF. This is Sallen-Key, second order Sallen-Key filter circuit. A second order filter consists of two RC pairs connected in cascaded here. Y1, Y2, Y3 and Y4 are the elements of the second order filter. An improved filter response can be obtained by using a second order active filter. Improved filter response. This one is equal to, this is the voltage VB. The voltage at non-inverting terminal of the op-amp is VB. Later I will calculate VB value. This one is plus and this one is minus plus. This one is VB. Resistance R1, V0, resistance RF, RL, like that. This is the non-inverting op-amp configuration. In case of non-inverting op-amp configuration, gain AF is equal to output by input. V0 by VB. V0 by VB is equal to 1 plus RF by R1. Later I will calculate this VB value. VB means this entire network is hide Y1, Y2, Y3, Y4. For simplicity purpose, we use this one, VB. Therefore, V0 is equal to VB into 1 plus RF by R1. V0 is equal to VB into 1 plus RF by R1. Apply nodal analysis. Apply nodal analysis to this filter. This one, at node A, the node voltage is A. At node B, the node voltage is VB. Apply nodal analysis at node A. Apply nodal analysis at node A. At node A. This is the node A voltage is VA. The admittance is connected to that VA are Y1, Y2, and Y3. And adjacent node voltages are VI and VB. According to nodal analysis, the node voltage VA into Y1 plus Y2 plus Y3 minus adjacent node voltage is VB into Y2. Another adjacent node voltage is VI minus VI into Y1. Another adjacent node voltage is V0 minus V0 into Y3. This is the node voltage nodal equation, node equation at a point A. That voltage is represented by VA. VA into Y1 plus Y2 plus Y3 minus VB Y2 minus VI Y1 minus V0 V3 Y3 is equal to 0. From this expression VI Y1 is equal to VA into Y1 plus Y2 plus Y3 minus V0 Y3 minus V0 Y3 minus VB Y2 VB into Y2. That is equal to VA into Y1 plus Y2 plus Y3 minus V0 Y3 minus V2. VB is equal to, from this expression, VB is equal to V0 by A. VB from this, VB is equal to V0 by AF, where AF is equal to 1 plus RF by R1. VB is replaced by V0 by AF, V0 by AF. Where VA is the voltage at node A, where VA is the, where VA voltage at node A, voltage at node A. Apply KCL at node B. Apply KCL at node B. The node voltage at node B is VB. Identify the admittances connected to that node BR, Y2 and Y4. VB into Y2 plus Y4. The adjacent node voltage is VA minus VA into Y2 minus VA into Y2 equal to 0. Minus VA into Y2 equal to 0. Apply nodal analysis. Nodal analysis at node B is VB Y2 plus Y4 minus VA Y2 is equal to 0. Therefore, VA is equal to V2 Y2 plus Y4 by Y2. Y2 plus Y4 by Y2. We know that V AF is equal to V0 by VB. Therefore, VB is equal to V0 by AF. VB is equal to V0 by AF. Y2 plus Y4. VB is equal to V0 by AF. A suffix F into Y2 See the equation 1. This one is equation 1. This one is equation 2. In the equation 1, VA is there. This VA is replaced with Y2 plus Y4 into V0 by AF into Y2. Again, I will write here first equation Vi y1 is equal to V naught V naught V naught VA into y1 plus y2 plus y3. VA into this one is VA into y1 plus y2 plus y3 minus V naught y3 minus V naught y2 by AF minus V naught y2 by AF. This is the first equation. V naught y3 minus V naught y3 minus V y2 into V naught by y2 into V naught by AF. Here VA is replaced with this expression V naught into y2 plus y4 by AF y2 y1 plus y2 plus y3 minus V naught y3 minus V naught y2 by AF. Vi y1 is equal to AF y2 V naught y2 plus y4 LCM is AF y2 y1 plus y2 plus y3 minus y3 V naught AF y2 minus here AF is there minus V naught y2 square minus V naught y2 square. Y3 V naught AF y2 minus V naught y2 square. Simplify this expression. Vi y1 AF y2. In that expression, V naught is there. Vi y1 AF y2. Here that V naught here is there. Here V naught is there. Here V naught is there. V naught is the common term. Here V naught is equal to y2 plus y4 y2 plus y4 into y1 plus y2 plus y3 minus y3 y2 AF minus y3 y2 AF minus y2 square minus y2 square. Simplify this expression. Y2 is multiplied this entire one. Y1 y2 plus y2 square plus y2 y3 y1 y4 plus y2 y4 plus y4 y3 minus y3 y2 AF minus y2 square. This y2 square and this y2 square is cancelled. Here y4 is a common term. Here y4 is y4 into y1 plus y2 plus y3. Here y4 is there. Here y4 is there. Here y4 is there. Y4 into y1 plus y2 plus y3. And here y3 y2. Here y2 y3. Here y2 y3 plus y2 y3 into 1 minus AF, 1 minus AF. Last term is here y1, y2, y1, y2. Finally, we need that ratio V0 by Vi is equal to V0 by Vi. Reverse here. AF, this one is AF, Y1, Y2. AF, Y1, Y2. Vi into AF, Y1, Y2. Here V0 into this one. Arrange this one into simple, this form Y1, Y2 plus Y4, Y1 plus Y2 plus Y3 minus, not minus, plus Y2, Y3, 1 minus AF. This is the transfer function. Transfer function of the second order active low pass filter. Second order low pass, active low pass filter. Here Y1 and Y2 is Y1 is equal to Y2 is admittances. Generally we use impedance, or in case of impedance we use Y1, that is the reason 1 by R. And Y3, Y4. Y3, Y4. Capacitive admittance is equal to SC. Reactance is equal to 1 by SC. 1 by 1 by SC, that is SC. Therefore, AFS is equal to here Y1 and Y2 is equal to 1 by R. Y3, Y4 is equal to S into C. Substitute these values in that these elements in that expression, above expression. AF into Y1, Y2, 1 by R into 1 by R, 1 by R square, 1 by R square, SC, Y4 is SC, SC, Y1 is 1 by R, Y2 is 1 by R, Y3 is SC, Y2, Y3, Y2, Y3 is plus SC by R into 1 minus AF, 1 minus AF. After simplifying here, R square is the common term. AF 1 by R square AF 1 by R square 1 by R square 2 SC 1 by R plus 1 by R 2 by R 2 SC by R plus S square C square S square C square plus SC by R into 1 minus AF 1 minus AF. AF 1 by R square. Here 1 by R square is the common term. 1 plus R into R square S square C square R square plus SC by R 1 minus into R square. 1 by R square and 1 by R square is cancelled. R here cancel. Here that is equal to AF by S square, C square, R square. 2SC R plus SCR into 1 minus AF. 1 minus AF plus 1 plus plus 1. That is equal to AF by S square, C square, R square. 2 SCR plus SCR is 3 SCR. 3 SCR minus plus 1. AF by C square, R square plus SCR is the common 3 minus AF plus 1. See again, C square R square is the common term. AF by 1 by C square R square S square SCR 3 minus AF by 3 SCR into 3 minus AF by C square R square plus 1 by C square R square. That is equal to AF into 1 by C square R square. Here R is cancelled. C here cancel. S square plus S into 3 minus AF by RC plus 1 by C square R square. 1 by C square R square. This is the transfer function of the second order low pass filter A of S or H of S. Some notebooks representation is H of S. For a general transfer function, the transfer function of low pass second order system, electrical, mechanical, hydraulic or chemical, can be written as A of S is equal to AF WH square by S square alpha into WHS plus WH square. Compare these two expressions. WH square is equal to 1 C square R square. WH is equal to 1 by RC. WH is equal to 2 pi FH 1 by RC. Therefore, FH is equal to 1 by 2 pi R. FH is equal to 1 by 2 pi RC. And one more term is alpha into WH is equal to 3 minus alpha into WH is 3 minus AF by 3 minus AF by RC. Here RC is equal to 1 by H. Alpha omega H RC is equal to 3 minus AF. RC is equal to 1 by omega H. RC is equal to 1 by, from this expression, RC is equal to 1 by, that is by omega H, 3 minus AF. Omega H is cancelled. Therefore, damping factor alpha is equal to 3 minus alpha is equal to 3 minus AF. Take that the second order, AS is equal to AF omega H square S square alpha omega HS plus omega H square. Simplify this one. S square by omega H square plus alpha omega HS by omega H square plus omega h square by omega h square is 1. Put s is equal to j omega. A of j omega is equal to a by j omega by here alpha omega h square by omega h. S is j omega. Here omega h is by omega h square cancel here. Plus 1 plus 1 that is equal to j square is minus 1, that is minus omega square omega h square plus j alpha omega by omega h plus 1, that is equal to af by 1 minus omega by omega h whole square plus j into alpha omega by omega h. This is af j omega. Magnitude of that this transfer function is mod a of j omega is equal to af by square root of this one is entire term is 1 a plus ab, that means 1 by omega square omega h square whole square plus alpha omega by omega h whole square. This is the magnitude transfer function. That is equal to af by a minus b whole square, that is square root of 1 plus 4 omega h minus 2 omega square by omega h square alpha square omega h square. Here alpha is there, the frequency response for different values of alpha. Different values of alpha means here some overshoots are there in that frequency gain function. According to Butterworth, consider Butterworth that alpha is root 2. The response is ideal. The response is ideal. That means this is the ideal one. This one is cutoff frequency fh. Therefore, af by square root of 1 plus omega power 4 omega 4 minus 2 omega square omega h square. Alpha is root 2. That means plus h square. These two are cancelled. Therefore, magnitude of af j omega is equal to mod af is af square root of 1 plus omega by omega h whole power 4. For nth order, the nth order generalized low pass Butterworth filter, transfer function transfer function can be written as mod af j omega is equal to af by square root of 1 plus 1 by omega h whole power 2n. For n is equal to 1, first order filter. For n is equal to 2, second order filter. N is equal to 2, second order filter. Final designed circuit is this one is minus R1, RF, RL, V0. Y1 is resistance 1 by R. Admittance is 1 by R. Impedance is R. This one is capacitance C. This one is R. This one is capacitance C. This one is minus. Not this one is plus. This one is minus. This one is VI. This is the complete design circuit. Complete design of the second order active low pass butterworth filter. With this, the analysis is completed.